So as it turns out, this is one of the popular, the one that we saw right now is used to be one of the most popular biasing schemes for current mirror biasings. The next question that we need to ask ourselves is, how do I apply signal to this configuration, right? How do I apply signal? Because ultimately we would want to make it look like an amplifier, right? So what did we do in case of a common source amplifier with a current mirror bias? We found out a way of AC coupling the signal. We found out a way of AC coupling the signal to the gate of the common source amplifier, right? So we found a way of coupling our voltage source to this node. And how did we do that? We used a coupling capacitor, and we can do the same thing here. So basically this is what we did. Use a different color. So this was this Vi, this was Rs. Then we had to size this coupling capacitor. Let me call it C1 in certain way, so that almost the entire of Vi appears at the gate of M1. But that was also not possible all the time. What we had to do was do this, right? So if we choose our values of R1, C1 correctly, then it is possible to get the entire voltage swing at the gate of M1, and then it essentially becomes the same old common source amplifier topology, but now with a cascode configuration, right? Okay, fine. So now the one that the stuff that I want to draw your attention to is the following. So let's only concentrate on the bias part of it, with the assumption that we know how to AC couple the input and the output. Okay, so this is M1, so on and so forth. So let's say this is V naught. What is the minimum V naught that we have while keeping both M1 and M2 in saturation? If we keep on reducing V naught, which transistor is going out of saturation first? Note that this current is largely unaffected by the change of V naught, right? Since this current is largely unaffected by the change of V naught, then we can essentially say that if I reduce V naught, then transistor M2 is likely to go out of saturation, right? So to establish that, we needed to figure out what is the voltage at the gate of M2, and that is quite straightforward, because now we know that this voltage is 2 VGS, right? So what is V naught mean? V naught mean, so minimum allowable voltage of V naught is 2 VGS minus 1 threshold voltage, which is effectively equal to 1 threshold voltage plus 2 overdrive, right? So this is much higher than the threshold than the minimum voltage in a common source amplifier without all this cascode configuration, right? So for example, if let's say threshold voltage is 1 volt and overdrive is 500 millivolt, right, then V naught min effectively becomes 2 volt. Now when you are operating from a supply of, let's say, 3 volt or 3.3 volt battery, then this can be a problem. You are essentially saying that the output cannot swing below 2 volt, then substantial portion of the available output voltage is lost just to ensure that our transistors are biased properly. However, if we say that uh, uh, will not do this, let's do this. Let's say forget about these type of biasings, right? So let's forget about this type of biasings. So, and I bias this with, let's say, some VGS, right? What is the minimum voltage across M1 that I need to maintain? Overdrive voltage of M1, right? While the voltage across the VDS of M1 is equal to V overdrive, what is the minimum voltage that I need to maintain at the gate of M2? This should be VGS plus V overdrive, right? So what will be the minimum voltage at V naught? Minimum allowable voltage at V naught will be, so V naught min will be VGS plus V overdrive minus 1 threshold voltage, which is equal to 2 V overdrive, right? So which can be 1 volt with the example that what we just took, right, in the previous page. So definitely you see that if you have supply voltage limitations, then clearly if we can arrange our biasing circuit such that these conditions are met, then I can essentially allow the output to swing at a far lower, much closer to ground than I could have otherwise, right? So then now the question is, how do I get these voltages? Now one VGS is easy to get, so this is easy to get. So we can get VGS like this, okay? But how do I get the other one VGS plus V overdrive? So essentially what I am asking is, how do I get this voltage of VGS plus V overdrive using transistors and current sources, not by resistor divider, methods, right? So let's see. So what is VGS plus V overdrive is equal to, if I spell it out, this becomes 1 VGS becomes threshold voltage plus V overdrive, and we have another V overdrive. So this is threshold voltage plus twice V overdrive, right? Now we know how to generate threshold voltage plus 1 V overdrive, right? So because this is threshold voltage plus 1 V overdrive, but here we need threshold voltage plus 2 V overdrive. So how should I go about thinking about it? Now the trick to this is to recognize that the overdrive voltage is a function of W by L and I naught, right? So let's see, if I expand this, this becomes threshold voltage plus under root of 2 V overdrive is 2 I naught by mu n C ox W by L, right? And if I take these two inside, so this becomes mu n C ox W by 4L, right? Note that. So what does this remind you of? What does this what does this second term remind you of? It looks like this is a diode connected transistor having a threshold voltage of VTH, whose current is I naught, but its W by L is not W by L, it's W by 4L, right? So essentially this looks like a transistor. This looks like a case where I have this. I have I naught, and that this is W by 4L, right? So what will be this voltage? This voltage will be equal to this guy, right? So this becomes 1 threshold voltage plus 2V overdrive. And now that we have it, what we can simply do is connect these two together, right? So this is again one way of biasing, right? Since this is one way of biasing, so this seems to have solved the problem that we were facing in the previous architecture, where we had two diode connected transistors stacked one on top of each other to generate the requisite voltage. But the problem was the output, the minimum output voltage would have been uh, wouldn't have been as low as it could have been. But do you see a problem with this architecture? Not a problem per se, but do you see something that can go wrong with this architecture? I'm sure some of you might have already figured this out. The problem here is the minimum voltage at what is the voltage at this node at the source of M2? The voltage is V overdrive. What is the voltage at the gate or rather at the mark those transistors? This is M3. What is the voltage at the drain of M3? This is VGS. So these two voltages are not identical anymore, right? So this voltage and this voltage are not identical anymore, which means the mirroring of current from between these two branches will not be accurate, will differ slightly. So this type of biasings are okay as long as you are not looking for exact biasing, exact mirroring, but you are looking for wide swing and high output impedance. However, if you are looking for exact biasing, then this also needs to be modified a bit. So what I will show you next is an architecture which does the uh, which does exactly that. Due to lack of time, I will not be able to show you the derivation, but you can analyze it yourself to convince yourself that this indeed is the case. So what this network does is basically this up a bit. Is basically diode connect M3 from top, right? So this remains VGS, but now I have a possibility of biasing this node in such a way that these two nodes, that the drains of M1 and M3 are identical, and as it turns out you can do that using our good old diode connected transistor having aspect ratio of W over 4L. And we can see, right, here we can quickly have an understanding of why this works. So if this is if this is VGS, what is the minimum voltage at the drain of M1 that while keeping M1 in saturation? This will be V overdrive. What is the minimum voltage at the drain of M4 while keeping M3 in saturation? This will also be V overdrive. Okay. So what is the voltage that is required uh, at the gate of M4? This will be VGS plus V overdrive, which was similar to the earlier case, and that is why we have this architecture. Okay. right? And how, and what is the voltage now at the drain of M4? What is this voltage? This is VGS, correct? So as long as, so if we ensure the drain voltage of M4, right? So VDM4 is greater than equal to VGM4 minus 1 threshold voltage, we have saturation condition for M4, right? So which means that we have M4 is in saturation, correct? So which means what we need to ensure? We need to ensure VGS of M3, but if we assume all the sizes are identical, everything is W by L, so VGS is greater than equal to VGS plus V overdrive minus threshold voltage over good, which means we are looking for is a case where we are sizing V overdrive at a voltage which is less than the threshold voltage. So as long as we honor this condition of V overdrive less than threshold voltage, then all transistors will be in saturation, and the mirroring will also be accurate, and the minimum voltage at the output will be 2 V overdrive. So that is why this particular configuration is often called wide swing current mirror. Very popular circuit, quite useful, especially in low voltage design, where every 100 millivolt can be a significant portion of the power supply. I mean, for example, in today's modern technologies, we operate with a VDD of, let's say, 1 volt, 1.2 volt, right? And the threshold voltages are still of the order of 300, 400 millivolts, right? So if you bias with, if you lose one threshold voltage essentially is a significant portion of, is almost like 30% of the available signal swing. So we cannot do that, right? So that is why uh, all networks or circuits which enable us a lot of room for the output signal to move is often preferred. Okay. Okay.